This is a continuation of the last office hours. So I think where I left off was talking about this in cylindrical coordinates. The top surface that it hits is the top half of the sphere, and the bottom surface that it hits when we travel down the z direction is the bottom half of the sphere. So these are the top and bottom halves of those spheres. And what I was saying about this is that if you went ahead and evaluated this, then you would end up getting 2. So integral of this is just z. That's evaluated here and here, so you would get this plus this, or 2 times this term here. And if you look back at the other form that we did, so 2 times the square root, if you look back at the other form, you get the same thing here, right? So 2 times this form. So either way you think about it, you'll end up with the same result. Okay. For the next one, somebody just asked in general about visualizing setting up triple integrals in rectangular coordinates. And this is also a video about how to pick kind of the best order to integrate first. And so I've got the same solid here. I'm going to try integrating with respect to x first, and then y first, and then z first. So this is the most interior integral. But the solid is consists of 2 surfaces. So we've got x equals 4. That defines this solid. And we've also got x equals y squared plus z squared. That's going to be this paraboloid here. So from the side, it sort of looks like a bullet type shape. Okay, so with these, I'm going to integrate this first one here with respect to x first. And so I can think about kind of taking the line that starts at positive infinity x. So I'm sort of starting way over here, and I'm going to draw a line that passes through this solid. So the first thing that it hits is this plane, x equals 4, and then it's inside the solid, and then the next thing it hits is that paraboloid x equals y squared plus z squared. So for this one, if I want to figure out the bounds of x, my top surface, the more positive x1, is going to be x equals 4. And then this bottom surface that it hits is going to be x equals y squared plus z squared. Okay, for the next one, if we integrate with respect to y first, so kind of this is the most interior integral, then we can start at positive infinity for y. And as we travel through this solid, the first thing that we hit is sort of the left-hand side, or sorry, the right-hand side of this paraboloid, right? It never passes through the plane. It's sort of parallel with the plane. But it hits the right-hand side of the plane first, or right-hand side of the paraboloid. And then the second thing it hits is the left-hand side of the paraboloid. So I'm going to start using a color scheme here to kind of talk about the 2 surfaces. So in this example, first thing it hits is the plane, and the second thing it hits is this paraboloid, right? For this one, the first thing it hits is the right-hand side of this paraboloid. And the second thing it hits is right? This left-hand side of the paraboloid. Right. So you can picture it traveling through. When we define this, when it hits the right-hand side, this is kind of both sides of the paraboloid, but we're looking for y equals something, right? So here they were already set up to say x equals 4 and x equals y squared plus z squared. Here we need to turn this equation into something that looks like y equals. So I'm going to take this and rewrite it as y equals plus or minus the square root of, looks like, x minus z squared. And that's going to refer to this paraboloid. So if we think about what this represents, the plus side is our right side, the minus is our left-hand side, since those are the positive and negative values for y. One that goes on top is this right-hand surface. So I'm going to put that up here. And on the bottom, I'll put the negative version of that. The next one, I'll do this one a little bit quicker, but we're going to be integrating with respect to z first. So we're going to be passing through the solid, kind of starting at positive infinity z. The first thing it's going to hit in this solid is the top half of this, right? So it hits the top half first, and then it travels through, and second surface it hits is the bottom half of that. We can do a similar kind of conversion because we want values of z here. So we can say that z is equal to plus or minus square root of x minus y squared, where the top half is above here. Sorry, so z square root x minus y squared negative square root x minus y squared. As far as the second two integrals go, because we've only set up the first one here, so in order to do that, we want to think about using this line to kind of create a projection here. So I'm going to take this like a little flashlight and kind of put that on these lines that I'm making. And I can think about the shadow that would be cast if I shined a flashlight onto the solid. And for this one, if I shine a light onto here, the shadow that's going to get cast is going to look like a circle. Right, that's what's going to get cast on this, and that circle is a region, and you're going to use that region to define these two. So you could say this is, the radius of this one is going to be, let's see, x equals 4. So that means that's occurring when x squared plus y squared plus z squared is equal to 4. So radius of 2. So you could use something that's equivalent to polar coordinates, but I think for this one, since it's in the yz plane, you can say that z is maybe equal to plus or minus 4 minus y squared, right? And y is in between negative 2 and 2. So define a circle here. For this next one, if you picture what this light would do to this side, the shape that it's going to define is going to look something like that. Maybe easier to kind of show what this looks like. on this one. So same shape, just kind of rotated. But the shadow that's cast on this one, again, is just the region that you're going to be using to define these last two integrals. So whatever shadow you end up casting, that's the region that you'll have to define. I think that in order to choose the correct order for this one, you want to think about the shadow that you leave behind, and also think about what the two surfaces are going to look like. But yeah, you can kind of picture each of those and say which region would be the most difficult to define. But I think any of these choices would be fine, but this is probably the easiest out of all of them. Okay, for the last one, this is a mass problem. And so I'm going to draw a quick sketch of what I think this solid might look like. It's bounded with a paraboloid, and then the plane z equals a, where a is some positive number. They don't tell us what a is, so we just kind of leave it as a variable. But here's what that plane would look like, z equals a. This one is z equals 9x squared plus 9y squared. I believe this problem is, if they don't explicitly say that you should use cylindrical coordinates, this x squared plus y squared should maybe tip you off that that might be a good idea to use that. And it is symmetrical around the z-axis, so we have the kind of rotational symmetry that's good for cylindrical coordinates. Density is just a constant k, so we can apply that to our mass formula. So mass is going to be this triple integral over the solid S times the density, and then we'll use cylindrical coordinates here, but I'll just call it dV for now. So in this case, if I want to set up my triple integral, I'll leave myself plenty of room for writing any functions that I might run into. The density here is stated that it's k, and dV in cylindrical coordinates is going to be dz r dr d theta. Okay, z, and if we think about the bounds for z, conveniently they're already in the right form. So the top surface that it hits, right, using that same principle, the top surface that it hits is the plane, bottom surface that it hits is this paraboloid. But I'm going to just use the fact that I know I'm going to be working in cylindrical coordinates and say this 9x squared plus y squared is really just 9 times r squared. R in this one is a little tricky to figure out, so we want to think about that shadow, right, for our next two integrals, or the projection. It's going to be shown, so that's the shadow, and we need to figure out the radius of that circle, right? Theta is going to be between 0 and 2 pi, right, since it's a full circle, but if we want to figure out the radius of this one, we want to figure out where this shadow is occurring. And this shadow is occurring when z is equal to this plane. Well, it's really occurring when these two surfaces intersect each other, right? So this is happening at the intersection of this plane and this paraboloid, and intersections happen when we just set them equal to each other. So I'm going to set this equal to each other. Look at that. We're trying to solve for r, and we have some equation for r here. So this means that r is going to be equal to square root of a divided by square root of 9, which is 3. And I'm not going to do plus or minus here since I know that r has to be positive. So it looks like r for this circle region is, or this disk rather, is going to be between 0 and square root of a over 3. Hopefully now that you've got this set up, as long as you remember that this r is here when you're integrating, you should end up with something that looks nice when you try to integrate it, because you'll have an r from this, an r squared from this. You'll be integrating that, and that'll give you some nice r to the fourth and r squared terms that you can end up taking the square root of. But anyway, I'll leave it at this. I think the setup is more important than trying to solve this integral. So concentrate on being able to set these up, setting all the bounds up properly, and that'll be it for this one. So that was the last two problems. Good luck with your studying.